Hello guys, so we are going to continue the discussion with respect to our functions and transformation techniques, and in this video we are going to go more in depth in understanding about vector transformation. Already we have spoken about functions. In functions you have already seen that how we can map, what exactly is a function. It is basically mapping the elements of one set with the elements of another set, right? And we have also seen about the notation and what exactly this meant, right? In this video, we are going to talk about vector transformation. Along with that, we'll also be seeing multiple examples specifically to data science. Okay. So quickly, let's go ahead and denote a function. Let's say that here I have a function and this is basically mapping x and y, right? X may have different set of vectors, y may have different set of vectors. Okay. Now in this scenario, let's consider that I have a vector x, okay, inside this, and I want to probably transform this vector into y hat, okay, in my space of real numbers. So let's say that here we have a space. I'm just going to denote it like this, okay. I'm going to just denote it like this, and let's consider that this is denoted by, it belongs to a real number of n dimension. N dimension basically means it can be 1 dimension, 2 dimension, 3 dimension, up to us, right? So what our main aim is over here is that, let's say that if this specific point is a vector over here, we need to transform this vector to some other set, right? Which we also say it as domain, a codomain, right? So let's say that this is basically going to get converted to this y hat by applying this mapping function, which is called as f, okay? And here I will also denote something like this. R of n is basically going to, let's consider that this is belonging to a real number of m dimension, right? So we also specify something like this, right? It is given in most of the textbook, but here, just to make simple, I'm just writing it like this, but you can also write something like this, r to the power of m, okay? So this, we are just trying to convert into other set which belongs to the m dimension of real values, and here it basically belongs to the n values, right? So here, if I probably consider x dash, right, how we can basically denote, I hope everybody now knows about vector. We can go ahead and denote like this, x1, x2, x3, like this up to xn, okay? And here you know that x1, x2, x3 up to xn belongs to a real number, and it can be of n dimensions, right? As always mentioned, right? I'll not write n dimension over here because we are specifically writing x1 comma x2 comma that up to xn, it belongs to r. So this all actually belongs to the real number, right? And already we have seen some of the examples also with respect to this, okay? Some of the examples, let's say that I want to probably have a function. This is my function, and let's say I have a vector which is represented by x1, x2, x3, okay? Or I can also go ahead and write it as x, y, and z, okay? And let's say we want to probably map this to another function which looks like this, x1, not another function, another, you can probably say another set which is denoted by x1 plus y, comma 2z, right? Now in this scenario, what will happen is that if I take some values, if I take some values, let's say for this particular values, how do we denote it, with respect to the vectors? So let's say this is my f, okay? We will go ahead and denote. We will write our vectors, which will look in this way. Let's say x1 is 1, 2, 3, okay? So here I have a 3-dimension vector. Once I map it to function f, okay, then what is the kind of output that I'm getting? x1 plus y, that is nothing but 1 plus 2. And then I have 2z, right? 2z is nothing but 2 into 3, that is nothing but 6, right? So finally you'll be able to see that I will be getting nothing but, I will be getting 3 plus 3 comma 6, right? 3, 3, 6. So this is the vector that I'm actually getting after mapping this particular function. Now let's visualize this in a coordinate system, right? Now since this is a 3-dimension, let's consider this is my x1 axis, y1 axis, and z, right? So let's consider that this is my x1, y, and z. Now you know that x1 is nothing but 1, let's consider this is 1 over here. Okay. And if I consider y is nothing but over here 2. So y will be somewhere here. Okay. Let's say 1, 2. And z is nothing but z is 3. So it will be somewhere here. So if I just project this point over here, it may come over here, right? See, just try to imagine in 3 dimension how we are projecting it, right? So from the top end view, if you see, this is my point that I'm actually getting. And this is nothing but this is your 1, 2, 3 in 3 dimension. And let's denote this vector like x dash, okay? X vector x, I'm just saying. Now, after applying this particular function, you'll be able to see that what is the transformation we are able to get. So here, let's consider that this is my axis. I'll just consider this is my a axis and b axis, okay? Now here I'm getting a as 3. So let's consider this is 3 over here. And here I'm getting 6. So this is the new point that I'm able to get with respect to this, right? And this is nothing but this is your 2 dimension. And this is represented by 3, 6. And if you want to probably find out the length from the origin, you'll be able to find it out, right? Like this, okay? So in short, what has happened, if you clearly see, initially you had this entire vector, right? And if I probably denote this entire vector 1, 2, 3, it belonged to our real values with respect to 3 dimensions, right? Real number with respect to 3 dimension. This has been converted to 3, 6, which is my 2 dimension vector belonging to the real value of 2 dimensions, right? This is what we are basically doing. And this system is also, see, here we are just applying a function wherein we are converting or we are mapping one set to the other set, right? This process is also called as, since we are applying it to vectors, this is also called as something called as vector transformation. Okay, we also say this entire process as transformation, specifically in linear algebra. Okay, and here you could see that how this dimension has been mapped to this dimension. That is the most important thing. And over here, how we have basically mapped this by using the function that is given over here, right? By this particular function, right? And with the help of this function, you will be able to see that how we were able to map it. Okay. If you also want to write this with respect to notation, and there is also one more notation in some of the test books that I have seen, instead of just using f, they also say that since it is a transformation, we'll go ahead and write transformation, wherein we are converting the real numbers, which is of 3 dimensions, to real number, which is of 2 dimension, right? So this is how also it can be denoted. Okay, denoted, sorry, not donated, denoted. Now let's go ahead and see some of the examples why we specifically perform vector transformation, just to make you understand why it is important in data science. And then in the upcoming video, we will talk about some very important types of transformation that we will do. Okay. So in if I probably want to, first of all, give the definition of vector transformation. Okay. And this definition is really important. Okay. Just to make sure that you are able to also refer this whenever if somebody asks you, right? You should also be able to refer this and you should be able to answer them. It can be asked in the interviews and all if the interviewer is much more research oriented. So vector transformation refers to the operation that maps vector from one space to the another, often changing the magnitude, direction, or both. Okay. So here the scenario will be that they may also change the magnitude and direction, or both, right? So in this particular case, initially I had this particular direction, then I got this direction, right? It may be also that I may get the direction over here, right? It depends. So here you can see that the direction is towards this side. If you go ahead and see, it is towards this side, right? So this transformation are typically described using metrics and fundamental in various fields, including physics, engineering, computer graphics, and data science. But I'm going to focus on 2 important things, that is computer graphics and data science, right? In gaming industries, this kind of transformations are heavily used. Okay, heavily used. So first of all, what I'm actually going to do, I'm talking about some of the examples where these are actually used. The first example is nothing but it is called as scaling. Okay, scaling. Now scaling is a transformation, that changes the magnitude of the vectors. Sometimes it may be required that you need to change the magnitude of the vectors while keeping the direction, while keeping their direction same, right? So if you want to probably keep the directions same and you just need to change the magnitude of the vectors, at that point of time you can actually do scaling. Okay. Scaling is a very important easy concept. Let's say that I have a vector v dash, and for this particular v dash I want to apply a mapping function where I scale the vector by 2, let's say. So let's consider that my vector v is nothing but 2, 3. So if I'm scaling it, I'm actually able to get the value as 4, 6. Now in this scenario, if you just imagine, right, what has basically happened? Initially I had a vector which is like 2, 3. 2, 3 basically means, let's consider 2 is over here, 3 is over here, and I'm getting this, right? I've just scaled this to 4, 6, right? New scale over here. We have just scaled this up, right? But the direction is almost same, right? So this is nothing but this is my 2, 3, and just by multiplying with a scalar, I'm able to get 4, 6. Okay. This is the best example that we can probably give it. Now, why scaling is important? Scaling in data science is specifically used in 2 different ways. One is data normalization. If I want to normalize the data, let's say in some scale, I will be able to do it. And the second important thing is that it is used in computer graphics to resize objects. Right? So here, one example will be that just open your paint, put up any image and resize the image, right? Resize the image. So there also we specifically use scaling, right? The direction will be same, but what we do is that we change the pixels, we change the magnitude of the pixels in short, right? So this is the application part when we are specifically discussing about scaling. Not only this, we also apply, let's say I have a scenario where we need to rotate the images, right? And if you are learning deep learning, right, specifically we will do this task, which is called as rotation, right? Now in the rotation, what we do is that here we do a transformation. I will show you all these things visually also, right? In just upcoming videos. So here, the transformation that turns vectors around the origin, okay, or any other fixed point, you can just say, right? Now what does this basically mean, right? We'll just try to see, right? Just imagine that I have a vector v is equal to 1, 0, and it belongs to r square, 2 dimension, right? So obviously I will be able to see over here 1, 0 is nothing but 1, 0, right? It may be this point, right? Now in my case, the transform vector will be nothing but 0, 1. Now once I do 0, 1, what is exactly happening over here? Just think over it, right? It is basically showing a 90-degree rotation, right? Why do we say 90-degree rotation? Just rotate this counterclockwise, okay? Counterclockwise basically means this direction. So if you probably just rotate this in this direction, my this point will probably go over here, right? It will go over here. And that is the reason you get 0, 1, right? Initially, these two are the points, right? Then we just made it go towards counterclockwise. So this was the direction, we just moved it counterclockwise. And we could see that I got a new pixel where I have done a 93-degree rotation, right? Now, why this will be useful? It will be useful in deep learning image processing techniques. Some of the example, rotation will specifically be used in image processing. Let's say I want to rotate the image, okay? Image processing. Specifically in deep learning also, we do rotate images, right? Rotating images. One of the example over here. If you know about reinforcement, if you have idea about reinforcement, we train robots also, right? There are researchers there are some amazing companies who also train robots. So specifically in robotics, for adjusting robot orientation, right? Orientation basically means, let's say if there is a dog robot, right? So for dog, how it probably visualize the entire world, it will be in different orientation. If there is a robot just like human being, right? So there will be a different orientation itself, right? And let's say if I also have a 3D graphics, I also can use this technique for rotating the objects, right? Rotating the objects. So these are some of the examples with respect to this. Okay. Now one more example can be reflection. Okay, so the third types, one more application that I can probably provide you is something called as reflection. So vector transformation is also used in reflection. So reflection, what does it mean? It is a transformation that flips vectors over a specified axis or plane. Okay, flipping the vector. Okay, so let's say that I have a vector v, it is 3, 4, and we need to flip across the y-axis. Okay, so if you are flipping across the y-axis, what will happen? So if I have this 3, 4, so this is my 3 and this is my 4. Let's say that this is my 3, 4. I want to flip it. So flip can be like, flipping basically means this axis will be flipped. I can bring this particular point, let's say to here, or I can bring this particular point to here, right? So if it comes over here, it is nothing but minus 3, 4, right? We can also flip this. And again, here what we can do is that I can just apply a vector. I can just multiply or I can just apply a vector like 3, 4 is there, right? Let's say if I go ahead and say I want to multiply with minus 1, 1, 1. So once I do this multiplication, you'll be able to see that I'll be getting this value, right? Minus 3, 4. So this can be my function f of x. Right, so there is some kind of transformation techniques that we are specifically doing, right? Now where reflection can be used, again in computer graphics, where we are mirroring images, right? I want to probably do the mirroring images. In physics, we specifically do this for analyzing wave reflections. So wave reflections will be there, right? We can also use this, right? Again, some more techniques are there, and I hope you may have heard about this also. Sharing, right? So what exactly is sharing? Just try to Google it, and I hope you'll be able to understand, right? So these are some of the techniques, important applications of vector transformation. Now going forward, we'll just go ahead and discuss about a very important transformation technique, which is called as linear transformation. But I hope you got an idea with respect to all the different applications over here, right? So yes, this was it from my side. Again, my main aim is to explain you all the topics with respect to different examples.